Hi, and welcome to our discussion of atmospheric dynamics. Specifically, we're going to be discussing balanced flow in this PowerPoint presentation. So balanced flow is when there's no acceleration. We looked at in previous videos the three-dimensional equation of motion. We broke it down into the horizontal and vertical equations of motion. And the equations of motion say that there will be an acceleration as long as there's an imbalance between forces. And the forces that we looked at and we discussed were pressure gradient force, Coriolis force, gravity, and friction. If these forces, or a few of these forces, are in balance, then there will be no acceleration. So we're going to look at a few theoretical types of winds that have forces in balance. And of course, these are theoretical winds. Sometimes they happen in the atmosphere, sometimes they don't, but at least they give us an understanding for what's going on in the atmosphere. So the first wind that we're going to talk about is the geostrophic wind. And geostrophic comes from the Greek words or Greek derivatives geo, which means earth. Also, geo is a type of car. And then strophic, which means turning, so earth turning wind. So here is our horizontal equation of motion. Remember, this is just looking on a weather map in the north and south, east, west directions. And what this says is that the acceleration of the horizontal wind following the parcel of air depends upon three factors. And that's the Coriolis force, the pressure gradient force, and friction. Notice that from the three-dimensional equation of motion, we dropped gravity because gravity doesn't work in the horizontal. So the assumptions for the geostrophic wind are that there's a balance, and balance means that there's no acceleration. Now, an acceleration of the horizontal wind can be because of speed, or it can be caused by direction. Anytime the wind is going around a curve, technically it's accelerating because it's changing its direction. It's a vector. So if we get rid of the acceleration, it means there's no change in speed and no change in curvature or direction. Also, it assumes that the wind is frictionless. So where is there no friction? Typically well above the boundary layer, maybe a few thousand feet above the ground, all the way up into the stratosphere. So no friction and also no acceleration, which means that there's a balance between Coriolis force and also pressure gradient force. So looking at that, we can modify this to solve for the horizontal wind. And to do that, all we have to do is divide both sides by F, which is the Coriolis parameter, and that gives us our wind. Now this is the magnitude and actually also the direction of the wind if you know the direction of the gradient, but this tells us how strong the wind is, the geostrophic wind, assuming that of course the wind is straight and not going around any curves and is not in changing its magnitude or speed. We can break the wind up into its components, the geostrophic wind into its components, by just remembering the components for Coriolis and also for pressure gradient force in the y direction and also in the x direction. So based on that, here are some equations which show, of course, the acceleration is 0. And on the other side of the equation, you've got Coriolis and also pressure gradient force. So we can solve these equations for the wind components, which would be the V and also the U components. So we can figure out the wind in the east-west direction and also in the north-south direction, given Coriolis parameter, density, air density, and also the pressure gradient in the x and y directions. Now, what we're just looking at is the geostrophic wind components on a constant altitude chart. In other words, height is your vertical coordinate. And the last time we looked at weather charts, we didn't use constant altitude charts, we used constant pressure charts. So what we're going to do instead is we're going to do a coordinate transformation so that we have an equation that will work on a constant pressure chart. You remember the way we did that? We looked at this in the previous PowerPoint. We used the hydrostatic equation and substituted pressure gradient for height gradient. In this case, it brings in gravity, g, and now you have dz, dy, and dz dx, which is the change in the height of a pressure surface in the y direction and also in the x direction. Now those were Cartesian coordinates. Sometimes Cartesian coordinates are difficult to work with because you have to determine the magnitude and the direction using trigonometry. Sometimes we're lazy and all we want to do is figure out the magnitude of the geostrophic wind. And to do that we can use natural coordinates. Natural coordinates are really convenient. Remember that S points in the direction of the wind and N points 90 degrees and to the left of that. So we can look at how the pressure or the height gradient changes in the N direction. So here is the equation in natural coordinates for the geostrophic wind on a constant pressure chart. V is the strength of the wind, the magnitude of the wind. Of course, G is gravity. F is your Coriolis parameter. You remember that was 2 omega sine phi. And then dz over dn. dz dn is the change in height of a pressure surface, dz, in the n direction. How much does it change? How many meters? So in this case, z would be in meters, meters of change in height over the n direction, and n direction is also measured in meters. So actually z over n cancels each other out as far as units. Gravity is in meters per second and F is in per second. So the seconds cancel out, at least one of the seconds, and you're left with meters per second, which is the units that we use for the wind speed. It's meters per second, or you can change that to miles per hour if you like, or you can even change that and convert that to knots. And the geostrophic wind, the calculation that we did, usually is pretty close to the upper level winds if the wind is moving straight, if there's no curves, and also if it's well above the boundary layer where there's no friction. And finally, if the height gradient isn't changing too much so that the wind is just moving straight. Those were the assumptions for geostrophic flow. Straight flow, no curves, non-accelerating, and frictionless. So what we're going to do is take a parcel of air, put it in a pressure gradient, and see what develops. So let's say that we have a pressure gradient so that to the north you have lower heights, to the south you have higher heights, which means that the pressure gradient, or the height gradient I should say, points to the south, but the pressure gradient force, the actual force, is actually pointing to the north. Remember that gradients point to higher values and the pressure gradient force is the opposite direction, pointing from high to low. So we'll take that parcel of air and let it go. And this is what happens. Pressure gradient force is pulling the wind, or pulling the air to lower heights, but as it starts moving, remember Coriolis force is a function of not only the latitude and the rotation of the earth, but also the speed of the wind. So once it starts moving, that means Coriolis force is going to pull it to the right in the northern hemisphere. And the faster it goes, the stronger the Coriolis force is. Now pressure gradient force, as we've drawn here, is constant. It's the same everywhere on this chart, but Coriolis is increasing until finally there's a point where Coriolis force is as strong as pressure gradient force. And when that happens, there is a balance. And that balance we call the geostrophic balance. And this is your geostrophic wind. So you can see that Coriolis turns the wind to the right until Coriolis finally balances pressure gradient and it's moving straight parallel to the contours. This also happens in the southern hemisphere, but remember, in the southern hemisphere, the wind, or the Coriolis force, turns the wind to the left. So, to summarize, geostrophic wind is such that it flows parallel to the contours, with lower pressure to the left in the northern hemisphere and lower pressure to the right in the southern hemisphere. Another way of looking at this is the old Bayes-Ballot rule, which says that with the wind at your back, you'll find lower pressure to the left. And if you're in the southern hemisphere, with the wind at your back, lower pressure is found to the right. We'll continue on with our discussion of geostrophic wind and what we mean by no acceleration in the next video.